Theorem 6 got cut off, so this video might be a little choppy. I forgot to turn it on silent and my dad called. So let's take a look at Theorem 6. Let's see what I was at. Okay, so this is if you put t to the n in here, and you can show what happens. And you basically use Leibniz rule where you can bring in the dt to it. So basically it's here, and you bring it inside and do the derivative of this. So you take that derivative and you get this. And so that's what you're doing. You, because where was f prime? So, okay. So when you do that, dds, you get this form, right? You get the negative t. So then when you simplify it, you get that with a negative on the outside. Okay, here's your t f of t. So if you keep going in that manner, you get that form. You get the form of negative L Laplace transform t of f of ts. Okay, then to get this form, when this is to the n, you keep basically doing that over and over and over, and you use induction on n again to get the formula. So we're going to be applying it and developing these rules so we can use these rules to solve differential equations using this transform. And that'll be a little later. Okay, so let's look at an example. And again, this one's just written up. I don't want these to be too long, but you can try it. So let's try this example using what we know, because you know t, you know sine of bt, and you're putting t right there. So we know this, and so this must be then negative df ds of that. So you're taking that df ds, this derivative. So doing that derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So you get this. And that's basically it. So therefore you get this Laplace transform. Applying the formula, basically, you get that. You get SBS over s squared plus b squared squared. And so using some of these concepts and theorems, you get a bunch of these properties. We're not going to go over all of these. We went over linearity a little bit and constant multiple. We did this property, and then here's so we this is pretty much summarizing all the ones we just did. So we're going to be using these properties to take a Laplace transform, but also to apply it to other things. One more example I have written down. Try it on your own. Evaluate that and how to simplify it. So what you may want to do is expand it first, then apply the linearization. So you take the Laplace transform of each one. So you expand it, and then you do the linearization of each one, applying the properties. So it works out. Once you do that, and basically you're not doing any calculations. You're using the properties in the table to evaluate, which makes it pretty nice, pretty slick. Okay, next we'll go over inverse Laplace transforms. And to do that, you need to review partial fraction decomposition.